So this is my review of my third paper, which is Improving Scalability and Reward of Utility-Driven Self-Healing for Large Dynamic Architectures. So the problem this paper generally attempts to address is that there's generally a couple of ways in which systems are designed to be able to adapt. One is rule-based approaches, and the other is utility-driven adaptation. And these both have various issues, such as rule-based approaches are generally scalable, but they do not, they only produce minimally satisfiable solutions based on the decisions they make. Utility-driven adaptation is generally not scalable for large problems. So why is this still a problem? I guess it's already been said that the advantages of rule-based adaptation is that they're scalable approaches, but they result in solutions that aren't necessarily optimal. And with the utility-driven approach, they do result in optimal solutions, but optimization can be quite expensive, and it's often not very good at handling larger problems. It doesn't tend to scale well. So for related work, basically with rule-based adaptation, decisions for adaptation are based on conditions being satisfied. And with the utility-driven approach, optimization techniques are used to find optimal solutions, and they're guided by a utility function. So the main idea of this paper is that basically for self-adaptation, it will be related to architectural self-healing. So if there's problems, failures within the system, this paper will be based around how the system is going to adapt and heal itself. And the authors propose this solution is that we can combine the rule-based and the utility-driven approaches to produce optimal and scalable solutions. And they use a pattern-based approach which combines utility functions with rules and essentially enables the system to compute the impact of applying each rule to a utility, and then based on that knowledge, the system can determine the optimal sequence to apply adaptation rules for self-healing. So why is this better? Well, essentially it achieves the benefits of both scalability from the rule-based approach and optimal decisions for adaptation from the utility-driven approach, and it eliminates the drawbacks of both of those approaches as well, in that it can provide optimal solutions rather than just minimally satisfiable or satisfactory solutions. And with regard to the utility-driven approach, it eliminates this thing where essentially the optimization techniques used in normal utility-driven approaches are quite expensive, and that generally means the larger the problem, it doesn't tend to scale very well. So it eliminates this issue of scalability. So for evaluating this, their solution, they use this simulator to validate the performance of adaptation, or it's often used for the validation of self-adaptation performance. And Essentially, this simulator was given the capability to inject system faults, thus resulting in the need for self-healing to take place. The simulator emulates a marketplace for auctioning items, and the authors compared their solution against two approaches, one being the rule-based adaptation approach and the other being the utility-driven approach. And their solution achieved a considerably improved solutions to that of the minimally satisfiable solutions that the rule-based approach would produce, and this was with a negligible overhead. Sorry, I should have been on that slide. And their approach also drastically reduced the computation efforts for planning self-healing compared to the utility-driven approach when both performed optimal adaptation decisions. And so this attested to its capacity to be scalable. And I don't have any critiques for this paper, so that is the end of my presentation.